Hello all. It's been a while since I've last updated the YouTube video for the Houdini tutorials or Grasshopper tutorials. I have been busy a bit making some materials for the Houdini seminars and some books that I've written in Japanese. Yeah, if you're a Japanese speaker, you might be interested in some of the Houdini books that I wrote recently. If you're an English speaker, I would like to know if anybody is interested in translated version of it. Okay, so today, now all things have been done, and I got some free time now so I'd like to continue doing some tutorial videos on YouTube. Okay, so today I'd like to do a simple geometrical shape in Houdini. It's called Kagome tiling, or in mathematical term it's called trihexagonal tiling, and it looks like this kind of shapes, which you see a lot of these patterns in traditional Japanese bamboo basket, where you weave the bamboo together to make this geometrical shape. And well, so since we're gonna use Houdini, I would like to also be able to use any kind of geometrical shape, like complex shape, which could be the combination of convex and Hall geometries. So concave and convex geometries. So in order to do that, I had to dig in a little bit more onto this, how I can be able to make this kind of patterns with the weaving functions, using this underneath geometry, underneath rules. So I came into one of the teachers I know showed me this paper by three people, called Beyond the Basket Case: A Principal Approach to the Modeling of Kagome Weave Patterns for the Fabrication of Interlaced Lattice Structures Using Straight Strips. So it basically explains what I would like to do. Like, you have like this kind of complex geometries, and by having this, by applying some of the algorithms they're showing, you can create this kind of Kagome patterns on any kind of geometrical shape like these. Now in this paper, it is kind of explaining how to reduce the curvature so that it can be fabricated using the strip. But in my case, since I'm gonna use Houdini, and I'm assuming the weaving, the material of this one strip could be like a rope or something, so I don't think I really need to think about the curvature, so it could be more flexible in terms of shape. So I'll tell you how to do that. I'll tell you how this algorithm could work. So first, to make it simple, you have this kind of triangular shape, a triangulated mesh shape. So consider it, all the triangles are the faces of the mesh. Then first thing you want to do with this is to create a small triangle inside each triangle. So pick up the middle point of each edge of the triangle, then connect it together to make one single triangle on each of this mesh triangle faces, which could be something like this. So each black triangle has this lit triangle on inside, which connects the middle point of each edges. Now if you hide out those black edges, you can see that it already creates this trihexagonal tiling looking like this. So this is the simplest explanation how you can make this Kagome tiling pattern. Now, in order to make it weavable, since what you want to do from this geometry is to be able to weave like this. Well, this is shown in 2D, but if you look into the photos, actually what you want to do is to weave in. Weave the pattern like this, so that each strip be interlaced like these. So in order to do that, it's pretty simple to do this. If you know the underlying rules, what you just need to do is to, let's say this is a single hexagonal tile that I pick up from the previous tiling, like let's say I'm picking this hexagonal tile and looking into it in perspective. What I would like to do is to pick one of the triangle, like the small triangle here on the side, then in counterclockwise, or could be clockwise. In this case, counterclockwise, pick up each edges of the triangle. Then on the right side of the edge, when you look into the counterclockwise orders, pick up the right side of the edge and then lift it up a little bit like this. So 3 edges, and the right side of the 3 edges be lifted up like this, and do the same things for the other small triangles here, which will be like this. And if you hide out the red one, the original line, you have the weaving pattern. Simple as that is. And it could be applied for, and if you do the same things for a whole small triangles in here, you will be able to get this kind of shape pretty simple, pretty easily. So that's the algorithm itself is pretty simple. Now what if now there are situations that you want to use a complex geometries, complex mesh, such as like the Stanford bunny mesh that has convex and concave shape included in one geometry. And in that case, it's pretty impossible to just use hexagon for the shapes. Sometimes, I mean, it all starts from this kind of triangulated meshes, but once you make a small red triangle, you could have hexagon, of course, but you could also have heptagon, octagon, or nonagon, which means the number of the edges could be 6, 7, 8, or 9 in many cases. And many cases it's a mixture of these number of edges. So in that case, you will have more random shapes. Now let's see how I could make a weave pattern from that kind of stuff. Now let's see, you have more irregular triangulated mesh like this. You do the same thing, make the small red triangles inside a black triangle, the mesh face triangle, hide it out, and then let's try lifting up the right side of each edge on the small triangles in counterclockwise order. Do the same for the other triangles and hide out the red one, and it still works. So this means that the algorithm itself, you don't really have to change whether when the edges of the polygon is different. You can always use the same principles to create this kind of weaving geometry, even if you don't have these polygons to be hexagon. Could be octagon, could be nonagon, doesn't really matter. So keep that in mind. The algorithm itself is pretty simple, so creating it inside Houdini is also pretty simple in this case. So let's try that out. Okay, let's start from making a geometry node. Let's go inside and let's import some complex geometry like Stanford Bunny from Stanford University. Yeah, the geometry looks a bit small, so I'm gonna scale it up like 100 times. Since this geometry is a open source mesh, I'm gonna include it in the Git file. You can download it together with my HIP file. Okay. Now, the first thing you want to do is to clean up some of the triangular mesh here. I mean, it is pretty much clean right now, but I would like to make each triangle shape or areas a bit more similar to the other stuff, the neighbors. So what I'm gonna use is to use the remesh node, and let's connect that here. And I think it's a bit small, so let's control some resolutions by changing the target edge lengths here. Now, when you change the target edge length, maybe you want to control it afterwards, since this parameters could be really critical later on. I mean, more rough the meshes more less weaving you have, more resoluted, more high detail, more weaving you have. So let's be able to control this using outside or external parameters. I'm gonna make a null node and name it controller. Let's color it blue and add a float parameter called resolution. Maybe the resolution could be from 0 to 2, and copy this parameter inside this target edge length. Okay, now you can control the target edge using these parameters. Now, next thing I would like to do, or maybe I could also increase a iteration for the remesh to a bit, so that I could smooth out a bit more. I mean, 4 is too much since it's losing some details of the original mesh, so I'll keep it to 2. Okay, so there are some weird stuff here as well, but it's fine for now. You can also control it later if you want to do that. Okay, the next thing is pretty critical, which is the things that you want to do here. is to make a small triangle on each triangle mesh face, like this red line. Now, in order to do that, the first thing you could do is to use the divide node, which have a function called compute dual, which creates a polygon out of these triangle meshes. Now, this itself doesn't look like this kind of shape, but by changing a little bit of this shape, you can easily create or replicate this kind of tiling pattern. The method is to pick up each intersected points on the polygon, which have several neighbor polygons. What I'm talking about is these each edge points, I mean the points on the polygon. So each point has at least 3, I guess it's always 3. Each point have always 3 neighbor polygons, and each point have 3 connected edges, and pick up those connected edges, which means 3 edges, and get the middle point of the edge, then connect it together to make a triangle. And in return, by doing it for all the intersected points, you'll get the similar polygon looking like this. So let's do that in Houdini. So in order to do that, since we're gonna look into each point's intersected points, I'm gonna use a point wrangle for that, and I'm gonna name it just intersected. And let's write some code in order to do some calculations, right? Okay. Now what you want to do first is to add a middle point here on each edges. So let's do that. First, for each point, get the neighbors using neighbors function and vex. Oops. And let's create a single polygon, which could be a triangle polygon for each point, and using add prim function type of poly. Okay, and for each neighbors, pick up the point of the neighbors. So if you're looking at this point, what you want to have is the position of this point, the end edge, and the end point of each connected edge. So this one, and this one. And that could be taken using point function. And neighbors. Okay. And also, let's get the direction from this point, or from this the end point of each edges to the middle point. Okay, so, or maybe the other way, from the original point to the end point of each edges. So let's call it direction dir equals, so you want to go from the original point to the neighbor points. You can do that by position minus original point position. Okay, now the middle point position, I'll call it MPOS, will be the original point position plus direction times 0.5, which will be this point, this position, the middle position, middle point on each edge. Now this is just a vector, so I'd have to add it as a point, so I'll use add point at this position. Then add vertex, use add vertex to add this point to the polygon that I made previously here. So poly mpt, and last of all, let's remove the original point, which is the intersected points, which I don't really need anymore. So remove point pt num. Right. Okay. Now see, you already have this kind of pattern looking exactly like this. But as you can see, not all the polygons are hexagon. Some of the edges, this one has 6 edges, but this one, like this one has just 5 edges. Sometimes it has more than 6 or 5, like this one has 7 edges, and so on. So the pattern, the number of the edges is not regular, but as I explained in the algorithm on the sketch, there's no problem using this to create a Kagome weaving pattern. So let's do that. Let's try doing that. Now the next thing you want to do is to make a weaving pattern, right? So in order to do that, I'm gonna clean this up a little bit. First of all, right now there's a duplicated points on each edges, since I created using Vex. I created duplicated and double points here, because I started from here. If I created 3 points here, and if I create 3 points here, there are duplicate points here on each point. So in order to reduce that, I'm gonna use a fuse. Now you used to have 5,394. Right now you have 2,667 points. Okay, now next thing you want to do is to, if you look at the point information and if you look at the normal direction, you can see that the point itself doesn't really have a normal directional information. It does show something, but it's pretty random where it heads to. So in order to make it face outside the geometry, the original geometry, which is this one, let's use the ray component or node, so that each point will face outside this original geometry. So let's connect it like these, like this, and then set the method to project minimum distance. Then you could check the point intersection normal, which will set the normal position to the outside of the geometry, like this. Now this is necessary because I have to calculate the order of each triangle's point, whether if it's ordering on counterclockwise or on clockwise. Since as you can see, let me hide these a little bit. Each face is, you can obviously see that each face is facing pretty much randomly. Like some of the faces are facing inward, some of the faces are facing outward by looking at the color of the face. So which means that the point order is different for each flipped geometries. So we have to keep that in mind in order to use the counterclockwise rule in order to make the weaving that I explained in the sketch. Now, keep that in mind. Let's make another wrangle to create a actual Kagome weaving pattern. Yeah, I'm just gonna use one single primitive wrangle to create the weaving line. I'm gonna call this Kagome. Okay. Now let's see. So by using primitive wrangles, this means that I'm looking into each triangle meshes, these. And in each meshes, you obviously have 3 points, 1, 2, 3, for it, because all the meshes are triangles, all the primitives are triangles. So keep that in mind. Let's do some coding here. So now, first pick up the prim points, which you'll have only 3 points on each primitive. And let's also get some parameters, user-defined parameters called distance. This will be a height of the weaving, which is this height. So let's define it by the user. Maybe I can also parameterize it externally, like here. So, and it could also be called as thickness, since on the last stage I'm gonna use this to create a rope. So I'm gonna call it thickness. Maybe it could be from 0 to 0.2 or 0.5. Maybe it's too big. 2.5. Alright. And copy this parameter, then paste it into this parameter here. Right. Okay. Now that you have parameters, let's look into each points. This, and get the first point. Maybe I'll call it PT1. Oops. And I want to also get the next point on the point order, so I'm gonna get the I plus 1, but then make a modular of length of the points number. I would also want to have the next one. That will be I plus 2. Also make a module like this. Okay, so now you have the point number of 1, 2, 3. 1, 2, 3 for each primitive. But at this point you don't know whether the point order is counterclockwise or the clockwise. So you gotta check that out. And what you can do is to use a cross function on the trigonometry. That's the easiest way to calculate whether the face is facing upward or inward. So let's check that out. Okay, so first thing, you want to have the position for each point. So point pt1 vector pos2 point pt2 vector pos3 point pt3. Okay, and let's also make the direction two direction, which is let's make a two direction. Let's say I'm looking into this white triangle here, and this is 0.1, 0.2, 0.3. Let's have a direction from that goes from either maybe from 0.1 to 0.2 and 0.1 to 0.3. So let's create two direction, this direction and this direction. And having these two directions, directional vectors, you can use a cross function for vectors. So if the result is positive, then it's facing outward. If the result is negative, it's going inward. That's how you can use in order to determine whether it's facing inward or outward. So let's do that. Let's use that. Let's calculate that. Create first direction, which is going from position 2, so position 1 to position 2. The directional 2 will be pos3 minus pos1. Okay. Now, as I told you, let's create a cross of these two directional vectors. There are 1 and there are 2. Okay. And as a result, before doing that, let's also get the normal direction for each point as well. Maybe just 0.1 and 0.2. I'll explain it later. So norm1 will be point pt1 vector, norm2 will be point pt2. Right. And the reason why I just got the normal direction of the point is that semicolon. As you can see, each point has a direction going outward, and what you want to check is whether the cross vectors is going outward or inward. If it's going inward, and if you calculate the dot product together with this normal direction on each point, then the result will be positive, which means the cross vector is going facing outward. If the result of the dot product is negative, then it's facing out inward. So that's how you can calculate it. So let's calculate the dot vectors, dot product. Float dot equal dot. I'm gonna use the normal 2 together with the cross. And if the dot is more than 0, then change the dot to 1. Else change the dot to -1. Could it be, even if the dot product is positive, it's not always 1, because 1 means the normal direction and the cross vector is facing the same direction with the same lengths, but it's not always the case like that, so I'm gonna normalize it by doing this kind of operation. Okay, now you have the information whether the cross vector is facing outward or inward. Let's add a new point called mpt1 and add point at position 1. So you're looking at this point minus norm 1, which means going inward, multiply by distance, which is the distance you defined, could be a thickness, times dot. So if the triangle mesh is facing outward, then this point will just go inward because I'm using minus, negative, minus here. But if this triangle mesh is facing inward, then this point will go outward because that will be negative multiplied by negative. You see what I mean? And that's it for the point 1, newly created point. And you also want to have one more point in order to create a line. So let's say that this point has been moved to here. Then what you want to have next is to move this point to the other side. So if it's going this positive way, if this point moves to the positive direction or outward direction, you want to move the next edge point to the negative position, the inward position. Then that's what I'm gonna do. pt2 add point pos1, pos2 plus norm2 times dist times dot. Simple as that. And let's also set the color for each point to obviously see the difference whether it's going inward or outward. Set point at riv. I'm gonna name it col. I'm gonna use it later for the color value, and I'll call it minus dot. And set point at riv col and pt2 for a dot. So if one of the point is -1, then the other point will be 1, so that you'll have -1 and -1 and +1 for each point on each edge. Then finally create a line connecting to this newly created 2 points. So add prim polyline npt1 and npt2. Now you'll see that this white line has been created, and as you can also see, the original triangle mesh is no longer necessary, so I'm gonna remove it inside vex. So remove prim num including points. Right, and if you look at carefully, you can already see that the weaving is already done, right? And if you change the parameter, the thickness, Yeah, you can totally see that the weaving height or the weaving thickness is changing like this, and I believe there's no like mismatch for the connections here. It's always weaving perfectly like this. Now this is pretty much done for the basic algorithm. I'm just gonna visualize it a little bit more to make it a bit more prettier so that everybody would notice that it is weaving. Okay. Now, as you can see, I mean, I've created only lines, and actually these lines are not connected yet. These are all separated primitives if you check the primitive numbers like this. So let's connect that together first. So I'm gonna fuse the geometry first to remove the duplicate points here. Then use the poly path to connect all the lines. Ooh, does it show? Okay. Right. And now used to have 5,392 primitives, but right now you have only 99 primitives, which means you only have 99 strips in order to create this kind of complex geometry, complex bunny by weaving. Okay, now next part is the fun part. Let's smooth out this weaving because it's a bit too jaggy, or it's too straight polyline. Let's make it more like looks like a nerves curve. So let's use a resample and maybe set it to 0.07 or something to create a bunch of points like this. Also set it to interpolated curve, which will smooth out the shape like this. Looks cool. Looks nice. Yeah. Yeah, it does look like weaving. Yes. Now, let's look at the geometry spreadsheet to see the details. And let's look at the color attributes. You can see that the maximum is 1, minimum is -1, and I think it's always like that because it comes from the dot product. But it's also by using the resample this node, by using resample you also have the interpolated value like these, like the value from -1 to 1, which is pretty cool. Yeah, I mean you can just use it for other purposes, and before that you only had 1 or -1. So having these color value, I'm gonna simply use it for coloring, point coloring. So let's create a color node here. Oops, color node connected here. And for the parameters, set it to ram from attribute and attribute to col. And yeah, it already looks like it's weaving something, doesn't it? Let's make the background a bit more darker so that I can see a bit more. Yeah, looks like a punching metal. Some metal pattern. Yeah, this is already cool, but let's also give a thickness to this geometry or curves. So wire, poly wire, and connect it here. Maybe set the division to 16 and the wire radius to the thickness that I set previously, which is also a height of the weaving. paste it here. And right now the color is gone because I think it's because of the issue with the normal, so I'm gonna put the normal node on the last and hide these points, and voila, done. All created like a weaving bunny Kagome pattern on complex geometry like this. And if you change the resolutions, like if you want to make it more detailed, you can change it to detail like this. If you want to make it more thinner strip, you can do it like that. If you want to have more rough patterns like this, you can have it like this. Cool. And I believe if you use a rope-like material, you can also fabricate this like you see in this paper. I mean, if you want to use this kind of paper strip, you have to consider about the curvatures, but as long as you use a rope type material, I don't think you have restricted to any kind of shape. So yeah, also try that out in physically, not just in virtual. Yeah, I mean, I should do that myself. Okay, that's it for today. This is how you can create a three-dimensional complex Kagome weaving pattern on Houdini. And thank you.